You can control a wheelchair just by imagining moving your hands. You don't actually have to move them, you just think about moving them.
This is Tom Carlson, professor from UCL, one of the leading minds in the world of brain-computer interfaces. We're talking about a direct line between your thoughts and the outside world.
A cap on the head, these little electrodes, they're listening for populations of millions of neurons all talking at the same time.
You're potentially unlocking the technology for people to be able to read our minds.
Yeah.
This isn't the evolution of assistive tech. This is the beginning of mind-driven control.
When you put the cap on someone else, they're able to drive that wheelchair themselves just with the power of the mind. That's amazing.
Is there a very specific, tiny area of the brain where you're capturing that?
That's a really good question.
Non-invasive tech is setting a whole new landscape, whilst invasive tech gives us the raw signals.
When we're talking about Neuralink, we're talking about more invasive recordings. You're really close to the actual source of those signals, thoughts and things that you want them to decode.
If PhD level of intelligence becomes available via LLMs, how does that impact the work that you and your team do? Tom, thank you for coming along.
Thanks for inviting me.
You've taken on the low-hanging fruit of scientific challenges to work out how to integrate the brain with technology.
Nice and easy. Nice and easy one.
I'm fascinated to understand my kind of visual timeline and map of all of the fascinating technologies that we have going on in the world today. And this neural integration, machine integration, brain integration thing, trying to understand where to plot that on that visual map of our technology revolution, evolution that we're going through. And you're at the heart of it.
Well, it is a fascinating world. And I think my sort of position in this world is really looking at how we can interface technology with the brain in order to support people who can't use traditional methods of interacting with the world. But obviously, there's a huge ecosystem of technologies out there for brain imaging. We've seen it, from CT scans and MRI scans for sort of medical applications, and going into all different areas as well, where we can use it in a therapeutic kind of manner, so planning for operations and things.
Yes.
But I think where I'm wanting to go with the brain-computer interface is being able to actually interact directly with the world just by thinking, without needing to move any of your limbs or quite utter a phrase, for example.
And is this a similar world to the world in which Neuralink, which we've seen, Elon's been peddling that, so it's become a much more kind of widely or a better known technology?
Yeah, so I think Neuralink is kind of an evolution of research that was going on for many decades, but obviously having quite a bit of cash to put behind an idea can always speed things up. So I think when we're talking about Neuralink, we're talking about more invasive recordings. We do non-invasive imaging of the brain, so that's mostly because my students don't like me sticking electrodes in their heads. But there's the merits to both approaches. So if we go back to Elon, when we think about invasive technology, so the ability to stick a needle into the brain and measure the electrical activity of a single neuron or a population of neurons that are close to that needle. That sort of research has been going on since the 1950s for these sort of microelectrode arrays that you can put into the brain.
Right.
But more recently, the Utah array was developed, which is a microelectrode array with about 100 electrodes, very small electrodes, tiny chip that they can implant through the cortex just into the surface of the brain. And obviously the problem there is that you're puncturing the brain, you're causing damage to the brain, you cause scarring, you've got a risk of infection, but you're really close to the actual source of those signals, the source of thoughts and things that you want them to decode. One of the challenges there is that you've got these quite relatively rigid electrodes going into a small area there. And so something that Neuralink developed was these kind of very ultra thin threaded electrodes, so very flexible and can kind of weave their way in, causing minimal damage. The challenge that we have with things like Neuralink is that because it's this private company, we get tidbits of information coming out, but it doesn't go through that same level of kind of scientific peer review that's kind of open for the academic community to discuss. So, it's always hard to have a strong opinion on where we are with that. But it's super exciting because obviously when you've got a lot of money going in there, you can really advance it. You can spend a lot more time thinking about developing the technology. And obviously we've seen that there have been, to some degrees of success, some pilots using, when I say pilots, I mean not flying planes, but for piloting the technology in order to do relatively simple tasks like controlling games and things, just by thinking about movements usually. So you think about moving an arm or hand or something. On the flip side, what can we get if we don't have to bury into the brain, and if we don't have to be so invasive with our technology? Could that open up the technology to a broader pool of people who are not necessarily willing to have Elon Musk open up their skull and put one of his chips inside? For some people, that might be fantastic, but I think there's opportunities for choice, and other people that might want to use a brain-computer interface on a more temporary basis, or for just parts of the day, and not have that permanently listening to their brain signals.
Yeah. I'd imagine that's a huge part of the market, which would be much more open and ready to kind of trial that kind of technology. And so where are you at with that, the non-invasive tech?
Okay, so obviously there are challenges. So if you're non-invasive, you're further from the source of the signal, which makes it harder to work out what's going on. And actually, I was at a conference just the other week in Vienna with a student of mine. And before the conference, my PhD student, Zia, she went to explore Vienna and ended up at the Kunsthistorisches Museum, so the Art History Museum in Vienna. Right. And she was having a look around, and she came across this painting, which I'd like you to take a look at.
Okay, cool.
So, I don't know if you know this painting, but what do you see in that painting?
Ah, right. I see a whole number of kind of vegetables and wheat.
So this is actually a zoomed in part of a painting by Giuseppe Arcimboldo. He's an Italian painter.
Right.
And he painted some images using trees and vegetables. So that's actually the portrait called Summer. And if we zoom out, that's the whole painting. So what do you see there now?
I see a figure, a lady.
Yeah, so it's a person. And so in that previous zoomed in view, we had, you can sort of make out the jawbone, the cheek, a bit of the ear.
Yes.
And then so you can see that in quite detail in the first one. When you zoom out, you get the wider context of what that actually means, what those building blocks are. And so when we're thinking about those invasive recordings, we're getting really close to the fruit that we see in this initial painting here. And you can look at really the detail of what's going on. So maybe the detail of what you're thinking about with your hand, for example.
Yeah.
But you lose that bigger context, the bigger picture. Because at the moment, if you're going with an invasive electrode, we don't have them all the way through your brain, but just embedded in a specific region, maybe the primary motor cortex, if we're interested in movement.
Right.
Now, the beauty of coming out of the brain and using a non-invasive technique is we can see the bigger picture. So we might miss out some of those details, but we can see how the brain networks are talking to each other and what's going on more broadly. So another analogy that I like to use is a helicopter. So if you imagine watching a football match from a helicopter, you maybe can't see where the ball is. You don't get a really good picture of what's going on, but you can see the players kind of grouping around and running in one direction or the other. And at some point, half of the stadium seems to go crazy. So maybe there was a goal, or maybe they disagreed with what the ref said, right?
Right.
But you kind of can infer from that bigger picture kind of what's going on globally. Equally, you can go invasive. You can land that helicopter on the pitch really close to the goal that at the end that you're interested in, and you can see exactly when they get a goal. You can't see what's going on down the other end of the pitch.
Yeah.
And you're also now got a helicopter in the middle of the football match. You kind of look at them away, right?
Yes.
And so I kind of see those as the different ends of the spectrum.
Yes.
And I don't think there's necessarily one that is better than the other. It kind of depends what your goal is, and maybe they could even be complementary technologies.
So help me understand. You said there about reading the signals, so closer to the signals. What does that mean, and exactly how is the technology working?
So when you're thinking in your brain, you've got millions, billions of neurons that are all talking to each other by just sending a little electric pulse from one to the other. And depending on these connections, that will then cause different things to happen. So, that's causing a command that will then go down my motor neuron and go and actually control my muscles. And so these neurons are all tightly packed inside your brain. It's really dense. And they all have their own kind of role to play in different areas of the thing. But in order to grasp this glass of water and have a drink, it's not just thinking about the motor activity, but I have to have that idea that I wanted to drink. I need to formulate a plan of how to, get to that. I have to perceive the glass in the first place. And then, so there's a lot of activity over all parts of your brain coming together in order to perform that very simple action. But what we see in brain-computer interfaces is often we're just trying to decode a specific action or intention, and then we use that to then control the device. So that intention might be that I want to move my left hand, for example, and forget about all the context around it. And so if we're only interested in, do I want to move my left hand, or do I want to pinch, or do I want to grasp or something, then it makes sense to be, from my left hand, looking over my motor cortex on the right side of the brain, the opposite side, the contralateral side.
Right.
And if you get really close to that, then you can see there's a lot of neuronal activity at that point where I'm thinking of grasping. Whereas if I'm looking from the helicopter down at the football pitch, then I don't necessarily see that I'm wanting to do a pinch grip or a grasp. I can see that I'm thinking about doing something with my hand, but I don't necessarily have that high fidelity interpretation of what that is.
Okay, cool. And so if we think about Neuralink, my understanding, and I might have this wrong, is that Neuralink is focused mainly on understanding its thought to text. Is that right?
So I think I've been exploring a few different things. I think lots of the early examples that I've seen have been on, controlling cursor input for controlling a computer game and that sort of thing. But I think there are lots of people that are also interested in thought to text as well now. So the difference there is you're going to be looking at different areas of the brain as well. So we're also interested in my lab in decoding motor imagery, so the imagination of movements, but we're also interested in decoding speech imagery, so the imagination of speech. And as I said before, for motor imagery, we're looking across the motor cortex, which is kind of central strip of the brain.
Right.
Whereas speech, we're kind of looking more over this side in an area called Wernicke or Broca's area of the brain. And so, different parts of the brain have different roles to play. When we're looking at decoding something like speech from brain-computer interface, if you're really close to that signal, so you're invasively recording from there, you're going to have a better signal quality, so you're going to be able to maybe decode more than if we're further out.
If you go back to that point you were raising, though, around kind of intercepting, I guess, being the invasive approach where you're kind of intercepting a specific current between the two neurons. If you think about something like speech, being able to intercept and, I guess, integrate, interpret that, is there going to be a very specific tiny area of the brain where you're capturing that? Or again, is there several points which are formulating something like speech?
Yeah, okay, that's a really good question. And speech is much more complex than something like these reaching and grasping that are very kind of well-defined areas of the brain. If we're thinking about speech, you can think about sort of your inner speech, where I'm not talking at all, and you can just be mentally rehearsing some words or having a conversation with yourself in your brain, okay?
Yeah. Like I'm thinking right now, fuck, I'm out of my depth. Carry on. Okay.
But equally, you might be speaking now, which is not involving just the area of the brain to do with speech, but also you're moving your mouth, you're changing your embouchure, you're using your tongue, you're controlling your breath. And so you can see there's a lot more activity involved there as well. And so decoding speech can depend very much on the sort of paradigm that we're going down. Are you imagining the sound of that as well? Are we involving the auditory cortex, or are we just thinking about the letters of the words, for example?
Right.
So one of the challenges that we have when we're doing this is actually explaining to people or participants in these experiments how to think about the speech. So then what we would do is record some data from different areas of the brain, that maybe Wernicke, Broca, and possibly some of the motor cortex as well, with examples of them thinking about very specific words or phonemes. And then we use machine learning techniques to look at that data, spot patterns in that data, so that when they come up again in the future, we say it looks likely that they're thinking about that particular word or phoneme.
Right, with you. That's super interesting.
So yeah, so really what you're doing there, just to be clear on it, is that you are studying lots of those connections between lots of neurons, and then just identifying patterns between them to reverse engineer what the output was, so what that word was or that movement or whatever it might be.
Yeah, and in terms of the reverse engineering, we don't necessarily really know what's going on under the bonnet there, right? But we're looking for patterns in terms of temporal patterns, so patterns in time, but patterns in frequency as well, spatial patterns, so around the brain, and also sort of patterns between the brain. So where we have connections between the brain, we can look at phase differences, so where we see information being transferred from one part of the brain to the other, we see some sort of phase synchrony, for example, between those two elements. And so we can look at lots of different features in those brain signals, and then we determine which ones are relevant to that particular thought, whether that is thinking about a word, number or something, or whether that's thinking about moving a limb. It's the same kind of basic principle. It's just recording from different areas of the brain and giving different prompts to the participant.
But it's remarkable, isn't it, to think that we are all carrying around with us. We talk about technology externally and all the wonderful things that are happening around us, but we're actually all wandering around with what is probably the most advanced piece of technology known to us in the universe, and probably most complex, which is the human brain. Am I right in saying that?
It's certainly extremely complex and a marvelous piece of technology. I think what's really interesting when we compare it with technology that we think about is generally our human brain is really good at solving problems that state-of-the-art technology and AI still find slightly difficult, okay? Whilst AI has been gathering pace, if we think about image segmentation, we immediately know that this is a table and that's a table. But tables can come in so many different shapes, colors, sizes, forms. And AI kind of works a lot on basically having lots of examples and trying to extrapolate from that. But the human brain is really incredible in how it can adapt very much more quickly for these kind of problems. And yet we struggle to cope with huge amounts of data and stuff, which is things that AI can do really easily. So, I think we sort of have complementary superpowers of our human brain compared with what we're seeing in AI developments.
Yes. It's really designed to solve different problems to AI in many respects, although AI is trying to replicate as much of the human brain's capability and function, but on massive scales of data, like you say.
And just think about the huge amounts of energy that requires as well. So the human brain, it uses a huge amount of energy anyway, proportionally for us. I'm not sure, maybe 20% of our energy or something. Yeah. But that's a drop in the ocean compared with all of these large language models that we see. And so your brain is highly optimized as well. And it forgets information that's not important anyway, or blocks it away in the deep long-term memory that takes you a while to kind of bring back again. And that's also a challenge when we're working with brain-machine interfaces, because, as I said, we're looking at decoding specific patterns when I go to pick up that glass. But over time, our brain's optimizing. It's trying to reduce its energy usage. And so think about, do you drive a car? Yeah? So think about when you're learning to drive a car. To start with, it was probably quite stressful. You had like so many different things you have to think about, and you're holding onto the steering wheel really tightly, and there's like traffic going around, and you're feeling completely overwhelmed. And then fast forward some years, and you're able to have a conversation with a passenger, maybe drink a glass of water or whatever whilst driving, and you don't feel stressed at all, because your brain has kind of learned how to integrate all that information, how to deal with it in a super efficient manner. And that learning is going on all the time at different scales. But that means that your brain signals are changing all the time. And so if we're designing brain-computer interfaces to decode your brain patterns that are like picking up a glass, that won't be exactly the same signal in a month's time or a year's time, because you'll be learning new things and developing new skills and forgetting some things as well. So one of the challenges that we have is, how do we keep on top of that? How do we use all of that data and make sure that our brain-computer interface is adapting to your brain signals as they evolve as well? And that's really challenging, because we know from good sort of interface design, so thinking Donald Norman, for example, talks a lot about interfaces. It's very important that we as humans can form a good mental model of a system in order to interact with it. We need to know what turning that knob actually does on the fridge. It's going to adjust the temperature, and how much do you need to adjust it. If that system is changing all the time, the brain-computer interface is changing all the time to match your brain skills, then it's difficult for you to understand how to use that system. Imagine like a steering wheel on the car. If turning that amount on the steering wheel sometimes just nudges you a little bit, but other times does a massive turn, right? And so you've got, with the brain-computer interface, you don't just have the machine learning, you don't just have the human learning, but you have a kind of mutual learning process between the two systems, and they're always trying to play catch up with each other.
Wow, so it's a continually moving feast.
Absolutely, yeah. So it's not like you train the AI or machine learning and leave it and say, okay, that's your brain-computer interface. It's going to need constantly updating and tuning to you.
And is that because you are monitoring and mapping the patterns of signals, and you're not able to detect the individual characteristics of individual signals? Does that make sense?
So again, if you go really in the invasive route, you can get down to sort of what we call local field potentials, or possibly even single unit activity of individual neurons. But because your brain is changing over time, maybe that electrode damages that neuron, and after some time, so there could be tissue scarring and stuff, and then that neuron might not encode that same information anymore. And so then the brain-computer interface has to find out where that's now encoded, as your brain has kind of reorganized itself. We see this also in, say, for example, if somebody has a stroke, and so they may get hemiplegia, so half of the body they can't control very well.
Yep.
But with physiotherapy over a period of time, and by repeating exercises and lots of hard work, some people are able to recover a lot of that function. It might not be quite the same as it was before, but your brain has been damaged, and then it's relearning, it's remapping the connections inside that. So we're seeing changes in those connections between neurons and what those individual neurons actually encode.
When it does that, does it find new parts of the brain, and it circumvents the kind of damaged part of it? Partly,
yes. Everyone's brains broadly have the same kind of topographical sort of layout, so the same functions in different areas. But there are studies that show, for example, if somebody is blind, then maybe the visual cortex at the back doesn't use as much energy and maybe reorganizes to support other areas of the brain as well. Similarly, if you have a spinal cord injury for a very long time, it might be that parts of the areas that are responsible for encoding some of those motor movements, fine movements of the hands, might shrink inside the brain, whilst other functions might increase as well. So there is a bit of reorganization. And whilst we're younger, that's much easier to do. And as we get older, our brains become slightly less plastic, that it's harder to learn new things.
When I think about neural networks, okay, and we don't fully understand how they're actually operating, which is the scary part, I think, of these neural networks right now. They've got a general understanding, but actually how they're getting to the answer to certain things or addressing things, they don't really scientifically know that. Whereas a traditional computer, right, you get your server screen up, you can map exactly every action, every line of code, how it affects the output, where it breaks down, where it errors, right? And so it's a very binary kind of 0 and 1s approach to the issues or problems or successes of its outcomes. Do you see that same logical infrastructure with the brain, or does it look much more adaptive? Like it's not dependent on the individual neurons in a way that a computer is individual lines of code. Does that make sense?
Yeah, so I think neural networks are being inspired by the brain.
Yes.
Right? So the brain is hugely complex with so many interconnections that are being made and being broken all the time. And so neural networks are a kind of really cut down version of what we think roughly is going on inside the brain. And basically, simply, the neural network, you've got a load of inputs here, different examples of things that we're wanting to decode. So it could be also different images, for example, and mapping those inputs to potentially some labels to say this is an apple, a pear, a car, whatever. And then your neural networks are just these kind of nodes inside that we basically will fire at random different points, and there'll be a 1 or a 0. We can pull together, we can combine outputs from one neuron to another, we have another layer. And then over time, we can train that network and say, okay, if we've got these, how do we get these outputs from those inputs? And we can change the weights basically on all of these neurons. Equally, when we're doing these experiments, we can look to say, okay, what happens if you take a layer out where you can do an ablation analysis where you actually destroy some of that network and you see how well it still works even if we get rid of a bit. And that's a little bit like with the brain as well, where you can take a bit out and you can reorganize and learn from them.
When you discuss it, it feels like it's far more adaptive and more fluid, which I guess is the difference I think of between biology and physics almost, you know what I mean? Like there seems to be an adaptiveness and an organic way of solving its own problems.
Yeah, and I think the thing is that it takes time, right? And so in biology, it takes time for this adaptation to occur.
Yes.
And what we're trying to do in engineering these networks is trying to accelerate that whole process.
Right.
So how long does it take for a child to learn how to talk, right? It takes years, right, of experience of actually they build their vocabulary, and we're still increasing our vocabulary now. But what we want with these neural networks is that they learn everything super, super quickly without all of this contextual experience.
Yeah, which is what people are saying is the big blind spots of the models.
And also think about the data that they're training these large language models on. It's only really a tiny subset of human knowledge. It's stuff that's kind of out there on the internet is quite biased, and in some areas it's maybe not representative of the global population. And so I think we have to be careful about how we're interpreting the output from this as well, because it can certainly reinforce. It's only going to be as good as the data that they're trained in target.
Yes. If you think about that, they're also trained, I guess, on how to research, how to validate. That information is all available in the content they've been trained on. So I do wonder whether we worry about biases, and we should do. I'm not suggesting we should never stop on that front, but I do wonder whether that becomes a problem that it manages to solve as it becomes smarter, more advanced, because it's able to use much more scientific ways of determining and valuing the data that it's being trained on. Does that make sense?
It's an interesting idea. I'll be interested to see where this pans out. I think the challenge that we see a lot of the time in practice when we're doing any sort of machine learning is that when you've got a lot of data, that tends to dominate the smaller amounts of data, right? And so depending what data is actually going in there, even if there's some very good information about scientific methods and things, if that's being drowned out by the majority of other data that's there, then the machine learning method might be learning from that majority and ignore that minority. Yeah. And so it kind of depends very much. I don't know what's going on in training all of these very large language models. But if we think about it in the context of what we're doing in my lab,
yes,
we spend a lot of time around the table thinking about designing experiment protocols so that we're not going to be biasing the data that we're giving to our machine learning systems. So whether that's biasing it from the cues that we're giving the participants, that we're not priming them through a different modality and we're not encoding that, for example, by accident. But also, it's very difficult to find the ground truth when we're talking about brain-computer interfaces, because we don't actually know what you were thinking, right? So we can say, in order to train our algorithm, we want to randomly ask you to think about moving your right hand for a few seconds, and then your left hand for a few seconds, and then switch them around a little bit, and that goes on for way too long and it gets really boring. But for those seconds, there'll be some time when you're actually thinking about moving that hand, and sometimes when you got distracted because you had an itch, or you're thinking, oh, this is boring, what am I going to have for dinner? And your mind wanders, right? But we don't have any ground truth other than we know that we asked you to think about that, and you said you were thinking about that most of that time. So one of my other students is looking at how we can weakly label that data and say, this is an example of moving the right hand, but not all of the data in that chunk of the recording is actually about moving the right hand. And so we want to maybe train our classifier, but we need to have a little bit of skepticism on the data there. So some bits will be good data and some bits won't. And how can we incorporate that into our machine learning? Right. And so if we're thinking about that on that's a very simple situation where we're just decoding right hand versus left hand. If you explode that up to the size of what we're talking about with large language models, I'm not sure at the moment how they can discern between, that's a lot of data, but actually where's the useful information within that?
Do you know what? When I meet loads of people and we have these incredible conversations, very fortunate. And we talk about all different novel challenges, the energy crisis, the demands of cooling data centers, all sorts of stuff, right? Rarely do I hear a problem that I struggle to think we'll find a way of solving. I think you've just highlighted one of them, which is that I hadn't given any thought, but yeah, it must be the most difficult environment to control.
Absolutely. And so we have to try and eliminate as many confounding factors as we possibly can.
Yes.
And again, when we come back to the speech imagery thing that we were talking about before. So if I ask you to imagine saying a word, and we need to look at that recording, we need to know exactly when it was that you started imagining that word and stopped imagining that word.
Yes.
And it's very difficult to get the ground truth for that. But what we do, we also ask people randomly as part of the experiment to actually vocalize that word and to say it. And so then we can build up a statistical model of what was the delay between us asking them and them actually starting to utter that. And we can see the variance, so what's the jitter on that. And we have a better idea of the window when that person was actually thinking about saying that word. Again, it's not perfect, but we're trying to find ways in which we can kind of hone in on where the real useful data is.
That does sound like a real challenge.
Yeah.
and a minefield in terms of, like you say, trying to get that scientific. When you guys are thinking about trying to get real accuracy, the holy grail of all science, really getting to as much detail as you can and as accuracy of your data, non-biased data. That sounds like an incredibly tough challenge.
But it keeps us on our toes.
Is that the biggest challenge you have?
I think working with people is a big challenge. They're certainly very unpredictable. As I said, the learning aspect, I think, is probably one of our biggest challenges.
Right.
So getting the right good quality data and being able to understand when and how to update our classifier is really difficult. So imagine what we do a lot of the time is inside a controlled environment in our experiment, but we want to move away from telling you to think about moving your right hand, think about moving your left hand, so you can actually use these in the real world. We've got an example where you can control a wheelchair just by imagining moving your hands. You don't actually have to move them, you just think about moving them. But then when you're out in the real world, driving a wheelchair around, you've got lots of other information that you're being bombarded with that you didn't have during the experiment. So you've got visual stimuli, auditory stimuli, people coming around, maybe you want to interact with them or not. You might have some anxiety that you're going to bump into something. Has the wheelchair safety system seen these things in the environment? And at the same time, you're getting feedback about what your brain-computer interface is decoding from your brain. And so you're changing your brain signals to kind of compensate. And so what we really want to do is then when you're driving around in the real world, use that data that we're recording to then update our classifier as well. But there, we don't have that controlled environment. We don't have the cues of when we told you to think about moving right or left. And also, we don't know whether or not we correctly decoded it. But we have some other tools.
Okay.
So we're looking at other signals that we can decode as well. So one of them is called error-related potentials.
Okay.
So that's the kind of like when you're watching something and you're expecting one thing to happen and something else happens, you're like, oh no. But you don't need to vocalize that. Your brain automatically detects that response. And then if we can detect these kind of signals in the data set, then we know that something didn't go as you expected. And again, we can start using these signals to weakly label our data so that when we're retraining, we can go, something wasn't quite right there. Maybe, and if that keeps happening every time they try to turn right, for example, and it didn't turn right, then we can retrain the classifier on that particular.
So it sounds like you're at a kind of prototype level with the wheelchair.
Yeah, absolutely. So it's something that we've developed in the lab. We've got a commercial wheelchair that we've then stripped away some of the parts. We put our own instrumentation and sensors on that. And then we're able to test it in different, still relatively controlled situations at the moment.
Right.
So we've done experiments where we bring in people who are healthy, able-bodied people just to test that it's safe to use in this sort of situation. And then we've also tested with a few existing wheelchair users to get their feedback on it.
Right.
And we've worked with partners in France. So we've worked on sort of modular technology that they can test in their labs as well. And they've run some early clinical trials in a rehabilitation center. Again, they're starting to look towards using this wheelchair with people who cannot use another powered wheelchair at the moment, as I've said before.
Of the two challenges you mentioned that one of them is about the wheelchair, the horse, understanding its physical environment.
Yep.
And the second one is the neural interface with the person, the individual. Mm-hmm. Which of those two is the bigger challenge right now? Or are they equally?
They're different challenges.
Yes.
So I think in some sense, the environmental understanding from the wheelchair is possibly an easier challenge because it's easier to get that ground truth. We can train. There's a lot of sensor technology. There's a lot of ideas that we can borrow from autonomous driving and cars and things. It gets more challenging as you work in lovely environments like this that are cluttered, very nicely cluttered, but cluttered with all sorts of different chairs and objects around. And so trying to understand complex scenes is difficult, and is more difficult than trying to understand a road scene that an autonomous car might have to understand. And I think also, a wheelchair, it's a medical device, so there's a lot of certification around that as well. When it comes to the brain-computer interface side of things, the biggest challenge is that we don't have that ground truth on what somebody's actually thinking, and how those brain signals evolve over time is really challenging to cope with.
If you look at it from where you are from an advanced perspective right
Yep.
now, would you say that you're closer to cracking the kind of the human aspect of it, or the wheelchair? I guess you can't have spent as much time on the wheelchair as the human piece, right?
Yeah, so I mean, the wheelchair is I guess more incremental, building upon layers of technology that already exist.
Yeah.
Whereas the brain-computer interface, it builds upon the science that's out there, but it's a bit of a bigger step compared with what we have in the market already, for example. Yeah.
I remember watching a TED Talk some time ago, and I read up about it a little bit, which is one of the most fascinating parts I found around the brain and its relationship with the body. Mm-hmm. And you can correct me if I've got this wrong, right? But is that the brain doesn't know what a finger is, or what a nose is, or what tongue is. They are the receptors of data that are being used to translate and be processed by the brain. And so what's really interesting there is that when you talk about that kind of left and right, and then you talk about like when you first learn to drive, and then it just becomes incredibly intuitive for you. So I'm assuming that I'm sitting here thinking, wow, to steer my wheelchair, if I'm thinking about something else and I've got to go left, think left, or think right, grip left, grip right, that is actually, there's just a pathway for that actually to become intuitive as an action for the person that's using that technology.
Yeah, so I think some really interesting things here. So firstly, I think to some extent you're right. The brain doesn't know what its body is to start with.
Yes.
And so in sort of child development, they go through a phase called motor babbling, which is where the brain's just sending out these motor signals, and you'll see arms and legs kind of flap about, and the child doesn't really know why that's happening. Yeah. And then after a while, they spot, that moved. Every time I think about that, that's moving. That's part of me. And they start to understand that and form those connections. And that's part of the brain development, to learn the dynamics of your own body and how to control it, and which bits are you and which bits are not you. Similarly, when we're thinking about the brain-computer interface, we need to almost do the opposite, because if we're wanting to control a device, we need to look into the brain and say which bit's responsible for controlling what, and how does that work. And we don't really care about the exact brain signals that you're using to grasp whatever, so long as we can find a mental task that you can reproduce in a reliable way, and we can decode in a reliable way, we can map that to whatever we want to do. So the reason I do a lot of work with motor imagery is because lots of the target end users are people who have tetraplegia, so they don't have full control of all four limbs.
Yes.
And in severe cases, they don't have any volitional motor control of the upper limbs at all, which means that sort of part of the motor cortex is still there. That's functioning, but it's sort of become a bit redundant because you can't use it. So if we can tap into that part of the motor cortex, that part of the brain, and use the function that you've already developed there, and repurpose that, so we can imagine moving your right hand to say turn right, or move a cursor right, or something like that, then we can just use that as a starting point in order to have that conversation with an end user, to get them to think some reproducible thought that we can decode. And then over time, with the brain-computer interface giving feedback, they might actually change what the thought is. And so it might move away from think about the right hand to just abstractly thinking right, okay? but there'll be something going on in that part of the brain that then is encoding that thought. So it might be that they sort of change that thought over time.
Yeah.
But the key is, how can we do that in a kind of nice controlled way that the machine learning can keep up with the user?
With you. Yeah. So what we're talking about is that adaptive kind of nature of the brain finding its own path to solving the problem.
Exactly. And again, if we think, as I said, the brain, we've got billions of neurons there. When we're measuring from EEG activity, so we've got a cap on the head there. We've got these little electrodes. They're kind of like microphones, but they're listening for electrical activity instead of sound. And they're listening to kind of populations of millions of neurons all talking at the same time. So it's like listening, I don't know, in a cathedral when everyone's talking inside the cathedral, and it all kind of gets a bit blurred together. You can't hear those individuals. And so if you are doing a complicated task or a novel task for you, maybe it was when you're first learning to drive, you have a huge amount of concentration. There's a really strong amount of neural activity there. But as your brain optimizes, that the signal actually reduces because you're going to be using less energy. You're going to use a smaller population of neurons, which means that the signal to the noise ratio goes down. So it starts getting drowned out by the other things. So we really have to kind of tune that into what you're thinking.
Yeah, I imagine like an image which is kind of pixelating to create a perfect image.
Yeah.
By the time it gets there, it's found its most efficient route to achieving the task.
Yeah, but then it's the most difficult bit for us to decode because it's the kind of quietest, smoothest way of operating.
That's interesting.
Yeah.
So actually, it's easier to track
at the beginning.
Yes, new tasks.
Yeah, because you have to concentrate more to do that.
Yes.
So there's more neural activity.
Why do you think that is? So that's where we're entering into kind of consciousness and subconscious and the unconscious mind taking control of the command center in some capacity, I guess.
I guess it's that focus and attention to start with. And so obviously focus, attention, a lot of energy, which is going to be easy to decode. And then gradually you want to offload that. So less focus, less attention. It can kind of run in the background. Less energy. It's going to be harder for us to decode.
Do you think it all comes down to that kind of pattern recognition as well for the brain? So it has access to that most relevant pattern of what that neural pathway or whatever it might be to complete the task.
But I think that pattern will just be getting smaller and smaller, more streamlined. Yeah.
So it just continually optimizing it and creating the most optimal, efficient pattern, which is what makes the brain so efficient.
Yeah, and when we look at like muscle control and stuff as well, there's some work that says, you're not having individual neurons going down to control individual muscles, but it's organized in things called synergies, where you have groups of muscles that are coordinated in different patterns. So you might have a neuron that says activate this pattern, and a different neuron that says activate that pattern. And then, in music, it could be a few different chords or something. Yeah. And if you play all those chords together, then you get that reaching and grasping that we're talking about, rather than having to think about controlling every single muscle, because it's too complicated and you wouldn't have time to think about anything else if that was the case.
So you are the guy that sat in the room with the guys with the tin hats and the electrodes.
Yeah, I've sat with the hat on myself as well. I've spent lots of time driving around wheelchairs just by the power of thought.
Yep. Amazing. Yeah.
But other things as well. When you do that, there's that huge difference between sitting in a dark, quiet room with a computer cursor moving on the screen compared with, I remember when I was a postdoc out in Switzerland in EPFL, and we had done many sort of demonstrations in the lab.
Right.
And then one time, my boss at the time said, "Oh, Tom, can we do a demo? The director of the university is coming down. He's got these important investors coming along, and they all come in the room. There's like 20 of them, all wearing suits, and drives a wheelchair now. And of course, the pressure, it's crazy. And your brain activity, there's all this other stuff going on, and you're really stressed. But luckily, we don't just decode the brain activity and use it directly,
right?
But we use it in conjunction with intelligent robotics. So sensors, in this case on the wheelchair, to understand the environment and to make sure that I don't crash into the important people, even if my brain's going mad there. So,
I see. Okay, yeah. So combining all of these latest technologies.
Yeah. The other day, some of my students organised an online event,
Right.
talking to some of the BCI pioneers. So these are participants who have participated in implanted BCI studies in the US, where they've had chips put in their head.
Right.
They still have the pedestal connector coming out of the head. And we had this conversation with 3 of them online the other day, just talking about their experience of being a participant and of living with this interface whilst taking part in these experiments. And that was very interesting.
Yeah. What was their feedback?
Yeah. So firstly, I mean, like we know, the ability to control something in a nice experimental setting just by thinking is incredible. And so these are people that have high levels of tetraplegia, most of them. And so it gives them a new way of controlling that they literally just can't control things in their daily life like that. So one of them was controlling a robotic hand. One of them was controlling some computer software. One of them was even having some brain stimulation as well. But the challenge that they had is that they currently are using this when they go in for the experiments, but they're living the rest of their life not being able to use that device in everyday life because you need a whole team of people around to kind of support that. Yeah. And at the same time, they've got this connector sticking out of their head and they see people in the streets and they're like, hey, what's going on? What's happened? What is that? You know, I have to be careful not to knock it and things like that. So I think, that's quite interesting to think these people are doing a lot for science. So they're not directly benefiting from this as an assistive technology that will help them necessarily in their daily lives at the moment. Right. But hopefully in the future it will help others.
But they're part of the path of progress.
Yeah. I think something else that came out really strongly though was, as scientists with this, we're focusing very much on the functional gains that we can get. So how can we get people to perform these movements again, or to reach and grasp or perform activities of daily living. But one of these pioneers, Galen, said actually it's not just that. It's the fun side, the creative side of things that I missed. I want to get back as well. And outside of the normal part of the experiments, the serious experiments that were going on, he was able to persuade them to allow him to control the tone, a musical tone, with one of his neurons that he had volitional control over. And this meant that he could create some music, not music as you or I maybe listen to the radio, but he could actually change the pitch of a tone. And for him, being able to be creative with that was really opening up new opportunities. And very impactful. I
can imagine that's so empowering in such a small way.
Yeah,
I can only imagine how that must feel. And also for someone in that situation, it's light at the end of a potential tunnel, whether it's for them or whether it's for next generation of people in that situation. Hopefully it will be for them and longer term. But it must be incredibly inspiring to be able to see and have that opportunity to be empowered.
Yeah.
Again.
Even some years ago, I was working, I think 2010, that sort of time maybe, there was a group in Würzburg, Andrea Kubler's group, who was working on a paradigm called brain painting. Right. Again, it wasn't functional for improving activities of daily living, but again, being able to express creativity and allowing people who had locked-in syndrome to use a brain-computer interface in order to control something a bit like Microsoft Paint back in the day. And so they could, creatively splat paint around this virtual canvas and express something that was, just creative.
That's incredible, isn't it?
Yeah.
So of the 3 people that you were talking to in that situation, did they have kind of full cognitive reasoning processing?
Absolutely.
Abilities?
Yes. Yeah. So they just had motor impairments, but perfectly reasonable, normal cognitive function. Right. And in the brain-computer interface community, for the experiments that most people are doing at the moment, they tend to be working with people with full cognitive function and some motor impairments. And that's for a few reasons. So one of them is informed consent. So obviously there are lots of ethical considerations of the work that we're doing, and one of the important basis for taking part in these sort of experiments is that we can explain what we're doing, why we're doing it, whether there's going to be any benefit or not. It's always better if we can get that informed consent from a participant. Now in science you can do you can still get ethical approval, and you can work with people who are unable to give informed consent themselves. But that's a lot more challenging. And I think let's start somewhere where we've got the possibility for informed consent there, so we can work with that. But also to understand the instructions that we're giving, because it can be really weird. Some of the experiment protocols, trying to understand what the task is that they actually have to do, is obviously much easier. And as I said before, it's already such a challenge trying to work out what's going on inside the brain. We want to minimize all the other sort of confounding factors. So, good comprehension, I think, is quite critical at this stage.
Yes.
Yeah.
Where are we exactly with that? So you've spoken about the wheelchair as the major application that you're working on. How far away are we from this kind of deploying this technology on a broader basis?
So the wheelchairs are really cool application. I really enjoy it. It's very tangible, but it's probably not the first application that we're going to. If we think, what do we spend most of our day interacting with other than people? It's probably a smartphone or something like that. Okay. If you have tetraplegia, it's already very difficult for you to get out and about, which does make it more challenging to have social interactions. And so being able to get onto social media or use a smartphone or computer is probably a much higher priority than moving around in a wheelchair. Yeah. Although, wheelchairs important and fun. So honestly, I think enabling that sort of digital access in a really, easy to use, intuitive manner is probably an earlier priority, because that opens up many more doors. Yeah. But we also see, prosthetics and orthotics could be a really interesting area for controlling devices, assistive robotics, wheelchairs, and these things as well.
If you're then getting it into if you're able to control a hand, for example, to regain that prosthetic hand, that actually solves universal problems, not just immediately a wheelchair, thought to wheelchair, is it? It's a kind of more universal application. Is that the way you have to look at it, actually? Yeah,
and if we go back to some of those other invasive studies that they've been doing in the US, the BrainGate trials, for example, I think one of those was on a functional electrical stimulation application area. And so that's not even using a prosthetic hand, but the idea there is that they create a bridge from your brain to your existing muscles. And so essentially they can put some electrodes around the forearm.
Right.
We do this in hospitals and things here anyway in the UK, and you can stimulate different muscle patterns around the forearm, and you can cause your flexion extension of fingers, for example, wrist extension. And then the idea is that you can link it up from the brain-computer interface to cause those movements. So without even needing to use a prosthetic device, you could potentially even still use your own body, but you bridge that gap.
That's incredible.
There's a group, a collaboration in Europe between a few entities. I think Clinatech in Grenoble and EPFL, I think, are involved.
Right.
Where, again, they've done a study using a minimally invasive module. So it's one where they're not sticking electrodes in the brain, but they are going underneath the skull. So they get closer to the brain. I think the device is called WeMagine. It's a wireless device, and that's coupled with a spinal stimulator. So they can think in the brain, and they can stimulate at the lower spine in order to generate or facilitate generation of gait patterns, allowing somebody to walk to some degree again, but in a very sort of supported environment.
Yeah. Coming back to that TED Talk that I watched a long time ago, don't know if you've seen it. It's the one where they they put a kind of number of sensors across the back
Okay.
of a patient or of an individual. And the objective is that it then captures sound, and that sound then puts a pattern through the back of the individual.
Okay.
And then that pattern starts to create some form of recognition in the brain and then starts to address hearing.
Okay. I've not seen that.
Have you not?
I've not seen that.
No.
But yeah, this is very interesting, this idea of sort of sensory substitution or sensory augmentation as well.
Yes, yeah, and that's where I was reading about this kind of sensory augmentation.
Yeah.
And it's interesting that they're kind of saying that they're giving an example where why can a bloodhound smell a cat peeing 150 yards away around the corner somewhere, and we can't? And actually, it's not.
I'm pleased that we can't, to be honest.
Absolutely. Actually, it's the receptor that's different.
Yeah.
And it's not necessarily the brain or anything that's going on differently there. It's just the receptor of that data. And they were kind of using that to then think about how do we, the future augmentation of technology, addressing some of the challenges that we have, is them thinking about how do we kind of create new receptors of data. That doesn't come into your field, really.
Well, it's on the periphery, I guess. So I'm aware of some of these things. I think certainly in the prosthetics world,
Yes.
One of the huge barriers to widespread use of more advanced prosthetics is that they just don't have the feedback, right? And so when you think about us, we can kind of be looking at each other. Again, we can reach that cup. We don't have to look at it, but we can judge the weight. We can grip it so it's not too tight that we break the glass, but we can support it sufficiently, and we can control all of that just basically by the power of touch and proprioception, understanding where our limbs are in space. And if you have somebody who's got an amputation and they're using a prosthetic limb, then they lose all of that feel of touch. They might appreciate the weight of something perhaps, but they lose that fine sort of feedback. And so there's a lot of research going on looking at sensory substitution and stimulation in order to, for example, stimulate peripheral nerves with electrical activity, so they can relearn, this is a soft surface or a cold surface or a hot surface. And it won't be the same original signals that they had, but thanks to that notion of plasticity in the brain, that ability to learn, then they can maybe eventually incorporate that feedback that's artificially coming from the prosthetic device itself.
That's really interesting.
Yeah.
How much of the work do you think that's being done in the humanoid area? Because obviously the moment that there's a huge commercial opportunity, it attracts shitloads of investment. And then we see, the science of certain technologies, accelerate exceptionally. And I think the humanoid space is something which I track. In fact, I've had Aaron Kidsey in here with a unitary humanoid. And when I see the rate of investment into that market, and I think about the success of that, the competition and the innovation in it is going to be around a lot of sensory-based technology. Will that be directly applicable into that prosthetics and into the medical space, do you think?
I hope so.
Yeah.
So my personal view is that we should be looking at sort of more human-centered robots rather than human-like robots. Yeah.
Right.
So we've got lots of humans around. I don't think we necessarily need to try and replicate them as humanoids. But I think a lot of the technology, the sensor technology and the processing could be applicable going across, especially into prosthetics.
Yeah, because I can't imagine that if Optimus, Elon's Optimus has the ability to pick an egg up and drop it in, cook, and do all those fine motor skills from a sensory perspective, that all of that technology will eventually kind of traverse into the medical.
Absolutely.
I mean, look, whether we like it or not, the fact that we're all sat there with an Alexa at home, or not all of us, but millions and millions and millions of people are sat in their homes. The moment that Alexa can walk around and do the ironing or boil a few eggs for us, there's going to be a massive demand for them. And
I guess the question is, do they have to be humanoid in order to perform these functions? Could Alexa be a robot that's functional with different robotic limbs and things, but does it have to be human-like in form?
Well, I have a view on that,
Yep.
which is that we've designed this world to fit in, for us to fit into it. And so I guess immediately when you think about it, if you were to design the perfect machine for optimal performance, it'd probably have wheels, it'd hover, it'd do all sorts of stuff. Probably have 8 legs, 8 arms, to be able to do all those things. But fundamentally, I guess if we want something to be able to start to do the tasks and to operate in our kitchen, as an example, they need to replicate the human infrastructure to be able to do that most universally. That's my view.
It's an interesting view. I think we can do better. I think we can build upon that. So
yes,
when you say, okay, will they have wheels or legs? Well, actually, for a long time, we've had these other things called WEGs, which are a combination of wheels and legs, and they're actually very good over all sorts of different terrain and they outperform wheels or legs kind of in a more kind of general purpose manner.
I see that as the evolution of it, actually, definitely.
So
why wouldn't it have 4 arms?
Because, that why not be better and complementary to what we are doing rather than trying to just replicate ourselves?
Yes.
We already have ways of doing that. It was coming back to that idea of humanoid robots. We have this kind of risk around trust. Have you heard of the uncanny valley as well?
Tell me.
So basically, we like things that as we sort of anthropomorphize them and they gradually become more and more human-like, we like them better and better and better until they get so human-like, but they're not quite there. There's something that's kind of uncanny about them. And then we don't like them at all until they're an actual human. There's like a big dip in that curve.
Okay.
It's called the uncanny valley. And I think it's quite important. If you're thinking about having a robot in your house doing these things, you're going to want to trust it to be in your house. I think, there's already some trust issues around having Alexa in your house and what she's listening to or not. Yes. Having a robot that can then actually physically do things in the house as well is, trust is a big issue there.
I said that to Aaron. I said, Aaron, I had a bet with him. I said, Aaron, within 10 years, I think this stuff's going to be indistinguishable from us. He was like, no way. No. I was like, we're too far behind. I'm like, look, I'm basing this on the YouTube video. So it's, he was in a far better place to really assess that. But I can't help but see the compounding technologies that we have and the evolution in so many different spaces that even if it's not 10 years, but you're right. I think the only anomaly to that, right, is AI. It's intelligence, right? Because does that get disrupted by the fact that we trust something that's smarter than us? And I see that happening already, right? If you look at kind of technology's journey, up until this point, technology has been a tool for humans to use and to improve, what they do, right? And we have been the master of it in most cases. There are some cases where we're not, right? But with intelligence, people are leaning into it as a higher power, a higher level of intelligence. They're seeking answers from it. And I just wonder whether the trust element, as it gets smarter and smarter, do people then build a different type of trust, which is far greater than our visual perception of it?
Yeah, I think this is a really important question. I think there's a huge risk with AI there because depending on how we define smart or intelligent, it might be or it might not be.
Yes.
So it's quite good at performing specific tasks that we've trained it to do, and it can learn some new tasks from that. But it's still not that sort of general purpose artificial intelligence that people are talking about. And with my students, one of the things, at UCL that we're always getting our students to do is to question what they're being told and have a degree of skepticism, a healthy degree of skepticism, and understand, the source. Where's that information come from? And I think that we can use AI in a healthy, responsible way if we still do that. But if we just start blindly trusting what it's telling us, I think there's some real big risks there as well.
Yeah, I agree with you. So that I think if you, I always have to take that lens off, right? So I'm doing loads of really critical thinking all the time around businesses and how it impacts others. Decisions we make big, impacts lots of people.
Sure.
We work in the care environment, for example. So, incredibly important. And so, but if I go back to your average guy, and I go back to where I'm from in Penzance, we spoke about this earlier, back in my hometown, those guys there, your average guy or girl that's just wanting quick access to information. And I think that the majority of people are leaning into it. They go to it for the answers. Do you know what I mean? Like that's, and not suggesting that's a good thing. I think that's just happening. You know,
that is happening. And I think it's, quick access to good, reliable information is important. But I think, we're still on that journey, and we need to think about how reliable that is. So some of these large language models are able to reference and tell you where the original information came from is helpful, because then you can still at this moment judge, that source of information, is that reputable or not? Do we believe everything that's written on Facebook or Instagram? Has this been published somewhere where there's a little bit of oversight? I don't know. Something that I read the other day that I thought was quite interesting is this development of, I forgot what it's called now, human commons licenses or something, looking at the equivalent of Creative Commons licensing, but for AI, to say, do I license this IP to be used by AI, and can it be altered or not? And then you can trace back to the source to say, okay, this was put out there with the intention that the author allowed that to be used and built upon by AI or not. I think it's going to be very challenging to police, but I think it's a starting point to sort of, I think Creative Commons was really interesting because it was a way of putting information out there in the public domain and saying, hey, use it with or without these restrictions.
Yes.
And then being able to trace that. I think there's a lot around explainable AI, which is coming out as well. And I think that will help with trust. But I think we have a responsibility to think about, the where this data is coming from, what the AI is being fed with, and, how it's making its recommendations.
Yeah, the biggest challenge with that is this kind of synthetic learning, isn't it? Even if you say, well, you're not allowed to reference this, it might not reference it. What it has done is it's extracted some principles of it whilst, marrying that up with some other principles of other data to create some synthetic data, this new view or very similar view to the one which we've had here. So it's the learning. You can't unlearn. That's the problem. Very difficult to unlearn, isn't it?
Can't forget that, yeah.
And that's what we're relying on in that scenario. And I think you're right. So it's important from a copyright and plagiarism perspective, really important that we start to get some control around that. And I think hopefully there'll be a lot of work that is done by the major platforms to protect. Zuckerberg came out and said that he kind of dropped it into some kind of really lengthy, like 50 or 60 page memo that they'd ingested 7 million books. And it was really interesting. It was almost like, I'm just going to drop this into here. So it's out there, but it's not kind of in everyone's faces. I'm not coming out as an explicit declaration of what we've done. Right. And it kind of just dripped out. But you do wonder, you go, wow, like just when you think about that. And there's a lot of fascinating questions that come off the back of that for me, which is, it just means that AI must know humans far better than we know ourselves.
Or an element of humans, right? The written down, documented side of humans, which misses out a lot of the other elements. So, spoken written word, it's only a tiny portion of communication. I can see your look in your face, you're trying to understand where I'm going with this, but you're communicating with me just by the way that you're looking at me, by your posture. All of this kind of information at the moment is not really captured in these data sets. It's a very small dimension of human experience, I think, that is being captured like that.
Yeah, and I'm hopeful about it. I wrote about it the other day, which is I had this experience the other day. I went to this fashion event, not that I'm interested in fashion, it just happened to have an invite, turned up, sat next to a fella, very quiet, like me, everything was going on around. He was just sat there and he got chatting away to him and he's like, oh, I'm having a drink because I know I'm going to have to speak to some people a bit later. I was like, oh, really, what you up to? We got chatting and we had this real connection around, we're talking about being definitions of being an introvert and an extrovert and where you get your energy from and all this kind of stuff. And it led into, then he works in tech and then actually he's just raised a load of investment and we're looking at kind of this, we made this introduction and we found this common ground, which, he left, asked someone, make sure you connect me with Ezra, and I said the same thing to someone else. And like, we're getting together to talk about some, doing some business together or helping one another actually. And I can't help but think that AI in the medium to long term will potentially amplify how valuable that is. Because you're right, it's not going to determine exactly, I'm not going to be able to make those connections in the same way. And historically, I was like, intelligent connection is just eradicating human connection. And actually, then I had this thing and it kind of put a lens over it. And I was like, actually, maybe this just gives us more time to focus on the human connections we value more greatly. And I think if you look at the world, if you look at the podcasting world or the way that, news channels are, disappearing and we're seeing, much more authentic public journalism and people are starting to build more authentic, different relationships with influencers or the world through different forms of media. A mate of mine, property developer, and he's got 2 or 3 influencers, newsreaders, people which are publishing content regularly on Ukraine situation right now, Ukrainians and Russians. He's got the same in Gaza, right? And he's got this myriad of people that he's trying to develop and get a balanced view of what's going on in the world. And I was like, it's amazing to think that 10 years ago, we'd have been reliant on Sky News or the BBC,
which gives you a very particular view.
Yes, yeah. And so I guess he's then building these relationships with people that he finds, and that he drops one he doesn't like or doesn't trust, or the ones that he does value come to the rise to the top. Where I'm going with that, it just comes to back to this: will AI actually provide us with the time to better value those connections, because they can't be replicated, like you say, from text and speak.
And I think that's a good use of AI, that you can be outsourcing the stuff that we don't need to be thinking about necessarily, the more repetitive tasks and things, and possibly remembering lots of stuff that you don't need to know on a daily basis, whatever. And synthesizing some data that you've already given it an instruction to do, fine. But I think that then you're right, that gives you time to spend with people. I think post-COVID, or peri-COVID, post-COVID, we saw lots of changes in the average workplace, with people working remotely. I work remotely for part of my week. I work on different campuses. I'm all over the place. But those conversations that you have in the kitchen or by the printers are nearly obsolete anyway now, or by the water cooler or whatever, are the really important conversations that you don't get at the end of a Teams or Zoom meeting or something like that. And you don't get from, the AI world, like putting all your documents together or whatever, making decisions. But if it frees up some of our time from these really busy lives to actually have meaningful interactions and conversations and embrace the serendipitous, and I think that's where the benefit really could be.
The thing is, if it's a one-way engagement, right, and so you're just getting some answers of stuff, it's very different to actually sitting there with someone and getting nuanced answers of someone that had that experience, and you're learning directly from it rather than from a synthesized perspective.
Yeah.
Right. And so you're then getting the nuances of the answer, and the difference between having 95% confidence in something and 100% confidence is mind-blowing. Do you know what I mean? Like the 95%, I might think about it and process it, give it some thought. If I've got 100% confidence in something that I've heard and it resonates and I've been able to qualify it and understand it, I trust the author, the person that I'm talking to about it, I'm ready to act. I'm ready to take action.
Yeah, and I guess at the moment what we see is perhaps a little bit of misplaced confidence in what AI can do because it's very convincing.
Yes.
Right. And so part of what we're trying to do at university is navigate this evolving world and support our students in being able to use AI responsibly and be critical about what's coming out from it and thinking about how to use that in a safe and responsible way and not over-trust the system, I guess. Yeah.
That brings us full loop back to that same point, which is it's a real danger. It's a real danger there, isn't it? Because, the critical thinking element, the journey is much more valuable than the outcome, right? So whether it's learning, experiencing, failing, if we're arriving at half-baked answers and we're not going on that journey, what impact is that having on us?
It kind of reminds me of talking to my granddad years ago about the invention of the digital pocket calculator,
Right.
And again, the data coming out is only as good as the data that's going in, and you need to have a guesstimate of what it is that you're expecting to validate that, okay, I trust the answer that calculator's giving me. But that's a really simple piece of kit compared with an LLM, where you still have to have that sort of guesstimate of what you expecting to come out from here, and does that seem credible or not? And, and I think, he thought the world might break because of the digital calculator and people wouldn't be able to do arithmetic anymore. But, it's a change in skill, and it's adjusted and we've coped with it and the world hasn't broken. And I think the same will be the case with AI, but it's a much bigger development. It's more rapid and we're still...
It's the scale of it, isn't it?
It is.
It's the scale, the speed, our lack of preparation for it. It's more like a endemic than a technology. It's like the rate of progression is just rapid.
But again, the incredible thing about humans is that we are really adaptable and resilient, and we come together and support each other. And I think, having open conversation, open debate, asking the right questions is important.
Absolutely. One thing I really want to understand, what were we doing putting needles and electrodes into people's brains in 1950? I mean, I don't know enough about it, but that seems...
Well, I think needles have gone into brains even way before that. But
Yes.
In the 1950s, that was when you sort of had the silicon revolution and people could start fabricating these devices on a really tiny scale. So they started creating these microelectrodes, so very small, that you could put in. And I guess... the challenge there is that the brain, as we said, there are so many billions of neurons in there, and you're wanting to target not just one, but you want to see a few different things that are going on. So it's not good enough just to put one electrode in and see what's going on. You need to look at kind of a volume, but you need to look at that volume in a really tiny space. And so this idea of having a micro electrode array where you have a 10 by 10 grid or something that you can implant sort of goes back to the 50s and has developed since then. It was more recently that they were able to fabricate such a device. I think it came out from that curiosity, trying to understand what's going on in the brain, but then also being able to use that information in a useful way.
At what point in time did the technology that we were using start to become really meaningful in terms of capturing enough data and for us to really thoroughly understand what was going on under the hood?
Yeah, I guess you get that sort of exponential curve. So it's hard to say there's like this turning point, but I guess maybe around the millennium sort of time, we started to see improvements in terms of computing power to deal with that.
Yes.
So improvements in terms of fabrication so that we can actually create the devices. It's just improving at such a rate at the moment. I think what we've seen, particularly in terms of the implantable side, is regulation and everything trying to play catch up, right?
Yes.
So I think they've recently announced the GB Prime study, which is going to be the Neuralink study in the UK. But that's obviously quite far behind what's been going on in the US because of the regulatory framework. It's taken a while to kind of catch up and allow these kind of experiments and to take place in the UK.
Yes. And I was with Ben Warner yesterday, who's a government advisor, and he was talking to me just to help me understand exactly how difficult it is to get change and how difficult it is to get the kind of, the 19th century operating system we call government to actually move forward and take shape. And I guess the fact that they've even got some studies in this area or they've made some initiative in it is really positive.
Yeah, absolutely.
Positive.
And I think sometimes it's good to have those checkpoints that do slow things down because it gives us time to pause and think and really sort of think, is this a good idea where we're going with this? Sometimes rushing headlong into something isn't the best idea. But equally, sometimes, we've shown that we can legislate and adapt very quickly. Like during COVID, for example, we're able to get things through clinical trials much more quickly than usual. There was obviously some controversy around that, speeding up procurement processes and things. Yeah, it's not without challenges. And so I guess it's getting that balance, right? What's the right rate of development to allow?
Yes.
Right?
And the risks of what you're doing, we're talking about, I guess, particularly the invasive space, but even the risks of the non-invasive aspect here is that you're potentially unlocking the technology for people to be able to read our minds.
Yeah. So I think we're a little way off there at the moment. I guess we are reading some specific thoughts at the moment.
Yes.
But we're far from that kind of pop a cap on and we'll be able to read all your intimate thoughts. So don't panic, we're not there yet. It takes a lot of, wanting to participate in this process, a lot of training on the user side. Yep. So I've talked before about learning to ride a car or something like that. It's that sort of level of commitment in order to learn how to use a brain-computer interface. There are different paradigms around, so some are a lot easier than others. So, for example, things like steady state visually evoked potentials, SSVEP.
Right. Okay.
And what that means is basically if there's a flickering light over there, and you're paying attention to it, you don't have to be directly looking, but you're paying attention to that flickering light, then you get a resonance in your visual cortex that we can decode. It just happens, okay? And so if you have a few different flickering lights around and you're paying attention to one of them rather than the other, we can decode that really easily. You don't really need to train for that. But if we're wanting to decode, as we were saying, speech imagery, inner speech, that kind of thing, we have to give loads and loads of examples that are specific at the moment to the individual. So there's obviously work going on to see how we can train a supermodel that would be able to translate from one person to another. Not in my lab, that's stuff that's going on in the US, but I think we're still far off from there at the moment.
What are the limiting factors, do you think?
So firstly, everyone's brain is so different, right? And we've all had our different experiences and things. The work that I do in the non-invasive space is very challenging because the signal to noise ratio is so small that it means, even if we go back to the same person day after day, the slight changes in the placement of the electrodes, whether they wash their hair or not, what shampoo they use, all these kind of things will change the electrical characteristics. So even if they are able to think exactly that same thought day after day, we won't get exactly the same electrical activity. So dealing with that noise is very challenging.
So that's a sensory issue, is it?
So yeah, because there's so much between the sensor and the source, the neuron, right?
In order to expedite that, it's the capability of the sensor that needs to improve.
Well, the capability of sensor, yes, but that there's still environmental factors. So
Yes.
as we said, like the skin, the scalp, the hair, these are all things that are independent of the sensor, right? So they are changing the electrical characteristics. If I shave my hair off, I'm going to have a different
With you.
different signal coming out. But yes, on the sensors, there's a lot of work that's gone into sensor development for invasive and non-invasive recordings. We have now in the lab, we've got active electrodes, so they're amplified really at the source of the sensor. There's a lot of work gone into wireless sensing as well, so that it minimizes the amount of noise that the cables from the sensor to the amplifier pick up and things like that as well. And then also, again, the more electrodes that you can put on the brain, you can do fancy signal processing to kind of like do a zoom in to different areas of the brain from that. Yeah.
How much more advanced would those sensors be than the sensors on, parallel technologies, which are being used? Like, I would imagine sensors like on robotic surgery.
They're different things. So, I mean, these are really just for listening into, for EEG, the electrical activity of the brain.
Yep.
But there's also a lot of development on looking at near infrared sensors as well.
Okay.
So I'm doing sort of direct measurements of brain activity. So we're looking at the electrical activity, but you can also look at the metabolic response of the brain. So we can look at the energy usage in the brain. And that can be done by looking at the oxygenation level of the blood in the brain. This is how MRI works, for example. MRI is not looking at electrical activity, but it's looking at changes in oxygenation of the blood. As different parts of your brain are more active, they require more energy, and so the oxygen changes. And so with things like MRI, you can actually look really deep into the brain, whereas with the electrical activity we look at, we're just looking at the surface of the brain. They're complementary ways of looking at brain activity. But we can't carry around an MRI scanner because it's massive, really expensive, huge magnet, quite dangerous. So there's other work, colleagues are working on this at UCL, but around the world as well, developing functional near-infrared spectroscopy, which basically you've got an LED that shines infrared light into the brain, and then a lot of optodes that then detect the refracted light coming out. And the properties of that light change depending on the oxygenation of the blood in the brain, the oxy and deoxyhemoglobin levels. And so by combining the EEG activity that I've been talking about so far with also this complementary way of imaging the brain, we can also hopefully overcome some of these challenges and improve the signals that we're getting. So kind of more multimodal imaging.
Taking a multimodal approach to
Yeah.
it. Yeah, the reason I was asking about parallel technologies, so are there parallel industries or that are using common sensors, is just to kind of get an understanding of the level of investment that might be happening in parallel to what you're doing. Right? Are there any other sectors in particular that are looking at electrical sensory?
Must be loads of electrical sensory stuff, but I guess it comes more like from radio frequency antennas and that kind of stuff.
Just maybe satellite stuff.
Except the frequency ranges that we're looking at are completely different. I'm just working this through, So typically we're kind of looking from 0 to 150, 160 hertz or something like that, which is extremely low frequency compared with, radio frequencies and things.
So trying to find something that's comparable to that is probably going to be quite limited.
Yeah, so a lot of what we're doing is looking at how we can process the data that we have. So firstly, try to minimize the noise, and then look at how we can use signal processing and possibly this multimodal approach to compensate for that.
Just coming back to the applications then, so are there specific applications that have you chosen specific channels? So the wheelchair is one. You've then spoken about the kind of, you've got some of your team are looking at the text and the speech to text kind of.
Yeah, so I guess really the application kind of grew out of my academic journey. So when I started off life as an electronic engineer. That's what I did as an undergrad.
Yep.
I then thought, oh, robotics are quite cool. Let's get a bit into that. And then thinking, is there something interesting that we can do with robotics for helping people, not just for, manufacturing and building stuff. And so I had the opportunity to do a PhD looking at smart wheelchair design. So I think at that stage, I'd read a report, and in the UK, I think it's about a quarter of the applicants for a electrically powered wheelchair in the UK were denied access to that wheelchair, not because of funding, but because they didn't have the required motor skills to control it, or they didn't have the required cognitive skills, or they had some sensory deficit as well, so partially sighted or something, for example. And so the idea during my PhD was to look at how can we compensate for some of this so that we can put sensors on a wheelchair that can understand the environment and compensate for any deficits there from the user so they can drive safely and efficiently around. And that kind of started off as quite a roboticsy type project. And then I started involving more potential end users in that. And so I came up with this idea then, building upon existing literature of shared control. So how can we interpret the user's intention in the context of the environment and then together control the outcome? So a little bit like riding a horse. So Frank Flemish came up with this horse metaphor for designing human-machine interfaces. You have an intelligent human being on a horse who can pull the reins and give the horse an indication as to where they want the horse to go. But the horse also can look around, perceive the environment, and work out exactly where to put each hoof. Yep. And together, they achieve something that either one might not have done by themselves. I applied that metaphor in creating this wheelchair. So the wheelchair is a bit like the horse. It can understand the environment, and it tries to understand what the human is giving it in a sort of noisy input signal. After that, there's a professor in Switzerland at TPFL who was working on brain-machine interfaces.
Right.
And going, we can decode some of the thoughts in the brain, and we're trying to control stuff, and wheelchairs are one of the things, but it's really difficult because we've got this relatively noisy brain signal. Sometimes it's right and sometimes it's not, and we're trying to work out how to do that. And so we kind of worked together on that, bringing the wheelchair and the brain-computer interface together. And we did some pilot clinical studies in Switzerland, which was really cool.
Amazing.
Demonstrating that it's feasible. And so I guess that's kind of the background. And so I continue that wheelchair work as a really interesting application area. As I said, I don't think that's necessarily the application for everyone, but it could be really interesting. I think trying to control a smartphone, being able to type is probably going to be more useful to more people as a starting point. And so that's why we're looking, part of our research in the lab is looking at and doing that as well.
Yeah. Right.
We've also played with other things as well, like telepresence robots and things, so that you can control a robot just by thought in a different environment and maybe interact with people in that environment, which is cool, but it's not quite there yet.
Yes.
Yeah.
What has been your greatest success achievement so far to demonstrate how advanced you've got to date?
Yeah, it's really challenging. But I think the coolest thing is when you put the cap on someone else and to start with, they can't do anything and it's really frustrating. But then after a few training sessions, they're able to, with a high degree of accuracy, control just moving a cursor on the screen. And you think, they're only moving a cursor on screen, but they're doing it just with the power of the mind. That's amazing. Yes. And then when you transfer them onto a wheelchair and they're able to, not 100%, not with fantastic accuracy, but they are able to drive that wheelchair themselves without any intervention from anyone else, that's really cool.
It's remarkable.
Yeah. But the challenge that I have is that at the moment we're able to do that in some carefully controlled environments, in a rehabilitation centre with supportive therapists around. Yep. So we're still quite some way to taking that out, driving down Oxford Street, yep, with a brain-computer interface. And
And what
so
are your biggest constraints to getting there?
I think, as we said, one of the things really is the reliability of the signals over time. It's changing. Even if you think of self-driving cars and things, the amount of investment and everything there, and they're still in such a relatively small area, and still even the was it the Waymo, the taxis, they still have a remote operator on standby just in case and all of that. So I think, when we're looking at assistive technologies, they're supporting people who are really in a minority, that are really struggling, and really where there's not huge amounts of investment and huge amounts of money to be made.
How much investment would you need to make a meaningful...
The offering.
but make a meaningful impact and accelerate the progress of the work you're doing?
Well, to give some examples, I've been involved with several sort of multi-million euro projects where we've been working on an element of that wheelchair project, for example. And we had challenges like moving from the work that I originally did to going to somewhere like Oxford Street. We had to deal with crowds of people, and so we were working with partners in Aachen in Germany that were able to use cameras not just to detect individual people but to detect crowds of people. We're working with collaborators in INRIA, in Rennes, in France, that could then model these flows of people moving around so that our algorithms could now work out where it's safe to drive that wheelchair around. And so that kind of got to a demonstrator level, but we're talking millions of euros just to get to that level. And then that's obviously not all certified, and you've got all the legal loopholes and things like that.
So it's a big investment that's required.
It's a huge amount of investment. But what I'm hoping, I don't know, if we think about other areas where we've seen change, back in the day, we used to have things called environmental control units for people with severe disabilities, severe motor disabilities. And these environmental control units would allow them to turn on a light or to open the window or to turn on a fan or something like that. And they were incredibly expensive, and they were bespoke, fitted to individual homes. Well, now we have smart homes that lots of people, not everyone, lots of people have them, and you can speak to Alexa or Google Home Hub or whoever you have in your home that can do some of these tasks that used to be very bespoke just for a minority of society, that were super expensive, have now become accessible. And so whilst I don't imagine everybody's going to have their own wheelchair or a brain-computer interface inside their brain, we might imagine that it could get picked up more, say, by the gaming community for non-invasive brain-computer interfaces, giving an additional input. And sort of if we're able to grow the sort of customer base for this sort of technology as a byproduct, we might then see people who need it for a healthcare sort of reason benefiting from that as well.
What's going to attract the investment in this is the transformation, sadly, from rehabilitation, where you are today, to enhancement, human enhancement and augmentation. So, the superhuman, the kind of where someone can see the path of this technology providing, becoming a commercial venture for everybody to gain, the ability to. I was sat here the other day and I was listening to some music. I don't have a post on it, actually. I was listening to some music. I was using ChatGPT and I wanted to use the voice command. Obviously, I had to turn my music off to do the voice command. I was like, 2025 has been the year of voice. I need 2026 to be the year of thinking.
So take out that step.
I mean, and look, I laugh and joke. It's about it, but fundamentally, the bigger the opportunity of the technology, it will attract investment faster, which solves the critical aspects of improving those people's lives in a rehabilitation phase, doesn't it?
I think we have to also be realistic about the promises of the technology as well. So because we don't want to sort of get that investment on false hopes in terms of the wider community. I think other areas where we might see some investment is more when we think about both in supporting rehabilitation,
Yes.
but also as assistive technologies. If that then enables people to get back to work or to reduce the amount of time that they rely on a carer, that then means that we potentially have an economic saving for them, but also that they can also then be contributing more to the economy as well. So there might be some elements around there as well.
What's your reservation of thinking to text limitation there? Is it, from you seem quite reserved or
no, so because we're doing this in the lab and it's really hard. So so what we're looking at the moment, big success, is above chance decoding of 1, 2, 3 different phonemes or different words, which is still quite far from that thought to text.
Yes.
When people have done more invasive studies or in a MRI scanner, you can get better resolution of that. So you can get decoding of full sentences and things perhaps as well.
Yep.
And so I feel that we will be able to get there to some extent, but I don't think we'll be there to the point where you're able to just decode in entire streams of thought. But it'd be more like thinking about keywords. I don't know if you remember sort of the early was it drag and dictate and stuff, the early voice recognition where you had specific commands that you could say and it wouldn't always get it right, but I sort of feel that we're kind of closer to that in terms of decoding non-invasively from bone computer interface, and in order to do that at the moment you have to wear this very sexy shower cap with all these electrodes and things, and it costs a fortune. And even the setup and everything takes some skill. It's not something you can just pop your cap on at the moment.
Do you see that as a limitation of the current technology, the way that we're trying to solve the problem? So infrared or new novel ways of addressing getting to the root data, I guess, the sensory data. I guess it's the existing technology, the limitation of that.
I think it's not just the technology. So obviously technology is improving all the time.
Yes.
It's thinking about the training protocols that we have, because lots of people nowadays just want to take something off the shelf and it works straight away without reading an instruction manual or training or anything, right? Yeah. So recognizing that it's not going to be that, and that there will be some training involved, and I think a lot of the work is really still done in science labs, in research institutes at the moment, looking at trying to solve some of those underlying fundamental questions with very few companies that are thinking about turning that into a product, which will look, the product will include elements of these technologies, and we could probably make a fairly rudimentary product at the moment, but would that then have success in the market at the moment without, I'm not convinced yet.
But I guess the way to think about that is that if you look at quantum, that's gained serious investment much way earlier than the point at which they had a stabilized product. Do you know what I mean? Like they can see the benefit. I just wonder whether because I see this as a foundational technology, do you know what I mean? Like an opportunity, I should say. Yeah, does that make sense? I see it as it's one of those big ticket things, which if you unlocked the power of it, it's a kind of gateway to significant, I can't even start to begin to think about its permutations and possibilities from an entertainment perspective, as a utility, whatever it might be. So I just wonder whether there's a tipping point at which, all the big tech guys and the players start to invest even more aggressively into this space. Does that make sense? Is there a...
Yeah, and I think that whilst there is the opportunity in the invasive world that we've seen, like with Neuralink, I think if we're going to go mass market, we're going to have to also look at the non-invasive space.
Yeah, absolutely.
And so I think that's probably where we're looking.
And will AI expedite? Is it already expediting or helping you?
Well, in some sense. I mean, we've been using AI for a long time before it became a are popular. Like
Absolutely.
lots of people are using AI as GPT type models or LLMs. Yeah, exactly. But we've been doing traditional machine learning for a long time, and we've been looking at these deeper neural networks as well. I think what's really exciting about AI with brain-computer interfaces is being able to get a better, richer understanding of the context. Okay, because when we're using a brain-computer interface, we're trying to decode a lot of these thoughts completely agnostic of the context, when in reality, if we understand the context, if we understand if it's a spelling thing, so thinking about predictive text, but imagine with a whole LLM around that, then we're narrowing that search space as to what we're actually looking for, which means we can be much more accurate in the decoding compared with if we're looking for any word that it might possibly be. And similarly, if we're looking at the wheelchair example and we're thinking about where we can drive the wheelchair, at the moment, you can look at all these possibilities and go, okay, well, you can drive anywhere where there's floor. But if we know that it's around lunchtime and this person seems to be on the way towards the kitchen, then we can already make it easier to go on that route. We can already be priming that in the decoding, right? So I think having this increase in the capabilities of artificial intelligence means that we can increase the context and we will be able to decode more accurately given that contextual information.
Yeah. You probably notice a lot of my kind of thinking is I'm always thinking about what innovation is happening in parallel work streams, industries, environments, which can expedite what's happening in other spaces. And so it's interesting to hear about like the sensory issues as an example. Like actually that is a pretty novel issue, with regards to the noise that's around it and the frequencies, and actually that means that the sensory technology is probably very few parallel industries using similar kind of technology. And then thinking about the long-term, benefits as to how far we are away from the kind of superhumans and augmentation and integration of technology we've seen in loads of sci-fi films. Obviously, we're more or less cyborgs already with the way that we're integrated to our phones. It's just it's just further integration. So just understanding that, I guess, is thinking about what the longer term scale of the commercial opportunities and how far they are away. Thinks about how quick investment can be brought into the area to address the rehabilitation needs and the medical environment.
Well, whether we're going that way or not, you've got people like Sam Altman and Merge Labs, I think, he's looking at trying to bring these kind of things together, AI and brain-computer interfaces. But we don't know many of the details there yet.
No.
So, yeah.
No, he's been quite vocal, hasn't he? He was saying that he thinks that the non-invasive route is the way forward.
Yeah, so or less invasive. I'm not quite sure how non-invasive. It's yet to be seen. But yes, I think that, how many people are going to voluntarily go through that operation? I think for people that need it for, medical reason, then that invasive route could be really helpful.
Yes.
But I think if we're talking about elective augmentation, probably not very many people will go invasive.
No, absolutely.
Yeah.
When the skepticism over just taking pills from pharmaceutical companies is on the rise.
Yes.
Allowing them to plug into us directly.
I know. And then you think, what we're talking about today, and data privacy and, who has access to that data.
Yes.
And there's definitely some ethical questions around that.
Yeah, I'm delighted the fact that these LLMs and these data centers need so much energy. Right, because all of a sudden
it's going to limit it.
No, but no. Well, actually, I think what it does, it's just going to expedite our routes to clean energy. Because you've got all the tech bros that are now just heavily in demand. It's attracting way more investment, and I'm really hopeful that will lead to fusion or other technologies, but giving us limitless clean energy in the future quicker.
Okay, the holy grail of energy.
Yeah. And look, I'm a tech optimist, right?
Yeah.
So when it comes to this, and so it's just interesting to see yeah, from that perspective, if it does hit the radar, so I'm delighted it's on Elon's radar. I'm delighted it's on Sam Altman's, and I guess there are other. We've got the glasses at Meta, again, which is kind of spatial awareness and stuff, which I guess would fit into some of that technology would be appropriate to the wheelchair. I guess all that kind of spatial.
Yeah, absolutely.
Kind of technology. So my passion and my curiosity is understanding how all of these technologies are supporting, complementing, innovating alongside each other, and in how they compound to create this crazy future that, is it 10 years? Is it 5? Is it 10? Is it 15? Is it 20 years before we start to see, synthetic biology and integrated neural interfaces and
well, I mean, so we do see these neural interfaces now, but it's just at what stage do they become more widespread, I guess. And as I said, people that have long-term implants, which is pretty cool, that they can have that implant for a long time, but they haven't necessarily been able to use it outside of the lab and to be doing things beyond that. So it'd be interesting to see how that develops as well.
Yeah, but implanted technology is is just also expediting, isn't it? And that can't be happening in silos. Do you know what I mean? There must be so much to learn from that. I saw that only this morning that there's now an implant which is improving sight, which is incredible, right? It's giving sight back to people which are blind and they can read again. And so,
but this has been a really long journey as well, and with sight, people have been looking at implanting at different levels, right? So whether that's retinal or on the optic nerve or in the visual cortex itself, and stimulating at these different levels. So yeah, I think it's really cool, but it's been a really long journey for that.
Yes, very long journey. Yeah, we can see these technologies just evolving. But there was one other question I was going to ask actually. Yeah, so the Google DeepMind's AlphaFold platform, that is being used by scientists, but I think predominantly biologists and chemists actually. Does that fall into your line of
not what we're doing? So I mean, they're looking at trying to explore massive search spaces really quickly and look for new ways of folding these proteins, which is computationally really, really intensive.
Yes.
The kind of work that we do is also computationally intensive. I guess one of the other challenges I didn't talk to you about was the amount of data that we have to work with, right? So when we think about AlphaFold and things, that's looking at really large amounts of data. Whereas when we're looking at brain-computer interfaces, because they are currently very individualized, all that data is coming from individual people, which means we have comparatively very small amounts of data. Right. And so our challenge is really, what data can we gather from larger data sets and what can we translate into supporting this individual and building a classifier that works for this individual. Right. And so, yeah, we did work with large data, but not on that same sort of scale. Yeah. Again, it can take quite a long time with all of our processing and things, but it's, orders of magnitude smaller, really, what we're dealing with there.
Yeah, with you. Yeah, I was interested to understand that, just to see whether some of the innovations in some of those parallel industries as well might be supportive of the work that you're doing. But again, you're just in this, mate, you've picked a fucking tough place to be.
Well, I wanted to make sure I still have a job, right? It's
you're going to be there a while.
Yeah.
I mean,
we're making progress.
Yes.
So, yeah, but it's been very exciting.
Yeah, it's incredible. Yeah, absolutely incredible. And what I take my hat off to people like yourself, the work that you do, is the commitment to it is exceptional.
Well, and it's not me, it's my whole team, and it's, mostly my PhD students that are really having, spending a lot of time thinking about this in the labs, collecting a huge amount of data from human participants, which is always challenging, very hard work, and then obviously doing all of the computation and everything as well. So it's very interdisciplinary. It's not just computer science, it's not just neuroscience, it's kind of mixing everything together.
And how many people would you have in working with you on this kind of topic at one time, would you say?
So in science, everything is a roller coaster. At the moment, I've got about 8 PhD students that are working in projects related to this. So some are more on, as I said, speech imagery, some are more motor imagery, some are looking at cognitive states, so looking at workload, looking at cognitive fatigue. Some are even looking at sort of supporting brain-computer interfaces to support mental health and well-being, and supporting meditation and things like that as well. So more in neurofeedback sort of style.
If PhD level of intelligence, it becomes available via LLMs and it's reliable and consistent, okay, how does that impact the work that you and your team do?
So that's a really big if.
Yes.
But I think that, obviously that would be really interesting in terms of being able to look at the data and give new ideas and sort of, a lot of the time that I spend with my PhD students is sat around the table discussing experiment protocols, discussing graphs and data and having a look and sort of thinking, okay, what tweaks can we make to the system to make it better? But another bit that they do is really hands-on physical, setting things up, tweaking parameters, having that sort of professional judgment during the experiment to work out what's going on. I think if LLMs get to that level of sort of reasoning, it could be very interesting in terms of generating new ideas and perspectives.
Right.
But I still think you need that human element in there.
Yes.
I think in terms of maybe it speeds some things up for them.
Let's project forward. Let's even say it's 5 years from now. It's not in the next 6 months or 12 months, but they reach that level of consistent level of intelligence. Your team are now tooled with that. How big an impact do you think that might have on the discovery and the success of their work or the improvement?
I think one of the most annoying things for a PhD student is to come to the end of some data collection. You're going through your analysis of that data and you go, oh no, if only we had recorded this other signal, or we've got this contamination or something, and we've just spent 20 participants worth of data collecting something that could have been so much more if we'd thought of this. But retrospectively, we can see that, but we didn't at the time. So as I said, we spend a lot of time kind of in the group thinking about trying to explore, brainstorming, what's the cost of adding this in? How much longer will the experiment take? And should we collect this? We have to think very carefully about data that we're collecting. But having an additional perspective and another AI PhD student in the corner that's also joining in that conversation and going, hey guys, why aren't you recording this? Or have you thought about that?
Yes.
Is probably where you'd get the value, where you're sort of thinking outside the box,
Yeah. The speed of thought around.
And sort of, just being able to mentally go forwards to, okay, whilst we're analysing, we're looking at all these things and, we might be missing this, but we could get that really easily. Let's add that into the experiment.
What else should I consider?
Exactly. Yeah.
Yes. Because the benefit of it, if it does reach it, it has this, is the data set when it gets there, right? Because, or if it gets there, we'll give you that. But it will then be its ability to think broadly as well as deeply, I guess.
If it can.
Yes, if it can.
That would be really interesting.
Yeah. You're at the heart of this, do you know what I mean? Like you're dependent on PhD level intelligence.
Yeah.
And so, understanding, when you're solving such complex challenges. But what I take away from this is is so much environmental. So it's great for great for perspective, great for processing stuff, great for creative thinking around it. But fundamentally, it's the application and execute the operational work where there's a huge amount of time goes into that.
Yeah, absolutely. And in different projects, I've worked with other people to support that. So physiotherapists and occupational therapists, and they come into the team and they help with some elements of that. But I think one of the other challenges that we have with the sorts of brain-computer interfaces that we're creating is that we can't just collect this massive data set like in traditional machine learning, where you've got a huge data set of images or whatever, and then you can put it out there and people can do these competitions and come up with the best classification they can for those images. Because when we're using data from the brain, that data has been generated based upon your current and past sensory inputs and experiences. And then whenever we then say, okay, now you're thinking about moving your right hand, and we give you feedback to say we've decoded that, you then might start changing and adapting your thought process that is influenced by our feedback that we're giving you, that comes from that brain-computer interface. And so being able to not just look at that offline data, but look at the data online when that human is in the loop. And then whenever you want to change that brain-computer interface that you're using, that algorithm, that classifier, that decoder, that's going to affect the brain signals. Nice. And so you can explore many different decoders on that offline data set, but to then try them in the real world takes a huge amount of time, because you need a real human being in the loop for that. Yes. And so we have to be really careful about what we're trying with real human participants, whether they're healthy, able-bodied participants or whether they're potential end users, because it's a huge investment of their time and energy to take part in these studies as well. And we need to make sure that we're kind of going down a promising route with that.
Yeah, it's great to get a practical understanding of how complex and challenging it is, the journey that you have to go on to achieve and get progress in the in your field. Hence, you're having to dedicate so much of your life and time to it.
But it's good fun as well.
yeah, that's it. And that's the one thing I pick up actually from the people, the scientists and the people that I've managed to spend some time with. Frank Verstrapper, who's he's the professor of quantum physics at Cambridge.
Okay, yeah.
And is this energy and passion and fun.
I think you have to have that. Yes. Otherwise, you wouldn't stay long. It's
weirdly, it's a bit like the NHS, really. We're indebted to people that, the average Joe public, you might not see this, but we are indebted to people like yourself. And we have been for many, many years, for all the people that have come up with dedicated their lives to all of the innovations and the improvements in health and well-being, and all of that comes from the science community. Well, not all of it, but 99% of it comes from the science community. So understanding, having an appreciation for the journey and how difficult that is very insightful for me, because I don't have that background. And and thank you for sharing it. It's really, really fascinating.
Well, it's a real pleasure talking to you, and I think everyone has their part to play at different points. If the world only had scientists in, then we wouldn't have any usable products at all, would we? It's kind of it's being then able to identify how to turn some of those creations into actual products that can be useful and help society, because a lot of the time, the scientist is aiming for 100%. Perfect system, which is going to take an infinite amount of time. And then sometimes you go, well, actually, do we need that in order to be useful in the real world? And sometimes for scientists, it's very difficult to kind of let go of that. And, so we need a balance of different people. I think diversity is our friend here,
Yeah. What's really also great, and is a gift you have as well, is the ability to distill what is an incredibly complex kind of concept and space, really, and be able to kind of keep me on that journey. I haven't felt completely stupid as we've gone through it. I've been able to track a lot of it. So thank you for doing that. And so I can't imagine that's not an easy feat. I mean, like boiling it down into something that people can try and follow and track. So
I think I just like talking. So.
You need to. Yeah. But how old are your PhD guys? Like what ages are they roughly?
So there's a range. Some of them have come straight from their undergrads, so sort of young 20s, and some of them have worked and have come, worked even in the NHS, and then have come out and are doing a PhD, having experienced life. And again, having that balance of different people in the team. some of which have been closer to kind of that academic learning, and some have more of that professional experience, I think is really important.
If I met them all, would I class them all as academic?
I think so. They are all academic, okay?
Yes.
But
Do you know what I mean by that?
So some of them have much more practical tendencies and want. I think myself, I enjoy learning by doing. I visualize things a lot. My wife likes equations and mathematics and stuff like that. And, I have to translate that into a graph for me to understand what's going on. And the same with my students. Some are much better at kind of wading through the equations and the code, and others like to visualize things. Others like to really be hands-on and practical. But we need all of these different pieces of the jigsaw to fit together, I think.
Yeah, the reason I asked the question is just because of what you said a bit about, you've got people which come at it from a practical kind of point of view.
Yeah, and I mean, some are much more on the computer science, machine learning side of things. Some more of the neuroscience, biomedical engineering. Some have more of the clinical and that clinical experience, clinical engineering, and
Yeah, I'm just super curious about these technologies, and I'm naive. Do you know what I mean? I just am. The reality, I'm not saying that from a being a modest perspective. I mean, I am just naive in terms of my understanding of how you go about your work, what's really involved in it, and I might say things historically which are kind of just too flippant or optimistic by not understanding the practical implications of progress in what you do. Does that make sense?
But I think that we all are to some degree, right? Because we all get in our little environments, our own little, I don't know, work cultures, and it's different from one area to another. And we sort of, sometimes you need to kind of come out of that and sort of think, okay, there are other people out there with different experiences. And I think it's really interesting, this idea for your podcast and bringing that all together. So,
if someone wants to reach out and get hold of you, how can they best do that?
Well, they can always approach me on LinkedIn, of course.
Great.
Thank you very much.
On LinkedIn. Thank you, mate.